Good morning, ladies and gentlemen. Our last lesson spoke about how current carrying wires generated their own magnetic field. Well, the fact that current carrying wires do have their own magnetic field means that if you were to put that wire within another magnetic field, it would feel some sort of force, based simply on the idea of action-reaction. So if an electric current can create a magnetic force on a magnet, then therefore a magnet can create a force on the electric current. Okay? And we're going to talk about today using the third right-hand rule about how to solve for the direction of that force. Okay? So a quick primer, the thumb again will be the current, or I. Our index finger, in fact, all our top fingers in this case, are going to represent the direction of the external, keyword being external, magnetic field. And rather than the middle finger, let's actually use our palm because it's just a little easier in terms of holding these things. But our palm is going to represent the direction of the force. So basically, whichever way the palm is hitting, that is going to be the direction of the magnetic force on the wire. Okay? Now, so that means over here is a good example. We see our magnetic field being pointing in a certain direction. We see our force, the magnetic force pointing in the direction. I know it says V over here, but V simply means the direction of charge. Okay? If we take again over here, you can see, therefore, if there's a wire carrying current, we would align our thumb with the wire. The B would now be the external magnetic field. We're not talking about the magnetic field created by the wire. That's the first right-hand rule. But in this case, there's an external magnet which ends up creating a force. So in this case over here, if we were to hold our hand, okay, the external magnetic force is being created by the north and south pole. We can see the external magnetic field pointing in this direction. So if we were to hold our hand with our right hand, it will look more like this. Our thumb points over to the right. And in this case over here, our palm will be pointing out of the page, which is what this represents over here, and that's why there's a dot. The magnetic force okay? And if you're dealing with an electron current instead, just like before, when you're dealing with negative charges, we simply use our left hand instead.
Magnetic field can be easily determined.
Okay. Let me just pause this for a moment. They have an electron current, in this case over here. So in this case, it's going this direction. In fact, if I were to represent that with my hand, with my left hand, I would use my left hand and show how it's pointing out of the page in this example. We have our external magnetic field going to the right in this example over here, B. So overall, because we have the electron flow coming out of the page, we have the magnetic field going to the right, my palm would now be pointing down. In fact, this wire would actually get pushed down.
Since the two fields are in the same direction above the conductor is repelled downward. If the direction of electron flow is reversed, then the field around the conductor also reverses.
In this case over here, they have the electron flow going into the page. Magnetic field is still going to the right. So when I hold up my hand, my thumb will be pointing into the page, my fingers will be pointing to the right, my palm points upward. So over here, I would have my magnetic force pointing up. And as you saw, the wire was pushed up as well.
Is placed within an external magnetic field, it will experience a force which is perpendicular to both the direction of the electron flow and the external magnetic field.
Okay, and this is just another representation of the hand rule itself. In this case over here, if I were to hold my hand, my palm will be facing up, my thumb will be pointing this way, and my palm will be pointing up, and the force will be coming up as well, because they're talking about an electron current. Now, this application of magnetic force is used in many different examples. We're going to talk about those examples from motors to rail guns. In this case, they show us the motor over here.
A current is placed between magnetic poles. If we apply the left-hand rule for force on this side of the loop, so that the thumb indicates the direction of electron flow, and the fingers indicate the direction of the external magnetic field,
you should be holding your own hand up at this point and practicing the left-hand rule, just to get a feel for this also.
then the force on the conductor will be upward as indicated by the palm. When the left-hand rule for force is applied to the other side, the palm indicates a downward force.
So because over here we have two different forces on each side, we can see how this motor, this basic motor is working. This motor is spinning because you have two different forces pushing in
Cause the loop to rotate about an axis until the loop is vertical.
Okay. So let's practice our left-hand rule just a little bit more. In this case, they show us the direction of the current and the magnetic field. It is an electron current, and they want to know what is the direction of the force. So with your left hand, okay, you should be having your thumb point to the left. Now, if this whole thing ends up being slightly awkward and you feel like you're going to break your wrist, an easy way is to simply turn your paper so that way it feels a little bit easier, okay? But otherwise, in this case, I can see that my fingertips aren't pointing in the same direction as the magnetic field. So I would simply turn it downward until my thumb is still pointing to the left. My fingertips are pointing down. I can see my palm is going into the page. So in this case over here, the magnetic force is into the page. Over here, they show us a magnetic field, and they mention that the force is directed out of the page. Okay, and since it doesn't say electron current, we're going to assume it's conventional current. Now they say the force, that's the palm, is directed out of the page. The magnetic field is going up. So in this case over here, when I hold my hand up over here, which way is my thumb pointing? And you can see it's pointing to the right. So overall, that means that my conventional current is going to the right in this example. Okay, sorry for the little break. I know I've changed clothing. Now over here, we are looking at another model of the electrical motor. And as you guys can see, using the hand rule, the force is always going to be perpendicular to the magnetic field and the direction of the current itself. This is used in another way. It's also used in rail guns, where we have a projectile, as you guys can see over here, being launched because of the magnetic force, which is also called the Lorentz force, acting on it. And over here is another picture of what that projectile might look like as being launched by it. Over here is just a more visual model. Because the projectile itself can also act as part of the current, you can see the magnetic fields that are being created by each side of the wire. It's pushing on the wire itself and projecting the projectile. And you think that this is not real? Well, maybe this is in Transformer 3, actually.
25.7 meters above sea level, 2932 north.
Kill track 5205 is
Target acquired. Killing track 2, 1.
Now, these speeds, you guys have to realize, up to Mach 7, okay? 7 times the speed of sound. And if you think it might not be real, well, here's an actual test demonstration done by the Navy launching the projectile. It's going so fast that the air is actually ignited by the friction of the projectile as it passes by. Now, when we talk about charges moving inside the wire, of course, usually we're talking about the electrons moving inside the wires. So it's not that it has to be carrying a current, but it's really that there's an actual charge carrying particle that's moving through the wire. It's actually the electron that's moving through the wire. So even if we move the charged particles outside the wire, they're still going to experience some sort of magnetic field, some sort of magnetic force. Okay? Still okay? So in the end, we're still going to use our hand rules for this. So in this example over here, if you take a quick look at this picture, whether we use the right hand or the left hand simply depends on whether it's a positive particle or a negative particle. So in the end, it still ends up being exactly the same, where we have the thumb as a V, which is really the direction of the particle moving. Over here, we have our magnetic field, the external magnetic field, and the palm, of course, represents the force. So if we go back to this picture over here now, in this case, we have an electron moving through a magnetic field. The magnetic field is going into the page. So if we were to use our hand rule over here, okay, I would want to point my thumb to the right because that's which way the electron is going. Of course, I would use my left hand. So my thumb will be pointing to the right, and my fingers will be pointing into the page itself. Okay? That means as the electron actually travels in, it's going to feel a force acting down. But what's interesting to note is that because the force is acting down, it does not change the speed of the particle. It only changes its direction. So in this case over here, the electron would start to curve. And notice, if the electron does curve, and now let's use a different color, if the electron's over here and going down, what's the direction of the magnetic field? It's still into the page. What's the direction of the magnetic force? Well, if we use our hand rule now, our fingers are still pointing into the page. Whoops. And my thumb is pointing down over here. So now my palm is pointing to the left, meaning this electron is going to curve some more. Notice the shape. The fact is, whenever a magnetic force is acting on a charged particle in a magnetic field, it's always going to be acting as a centripetal force, meaning that FB can equal to our sigma FC, so we can set that equal to mv squared over r. So the main thing here is that mv squared over r. There's a change in velocity because of the change in direction, but there is absolutely no change in speed. Okay. If we do another quick question below, just to practice this a little bit more, we see 4 electron beams, A, B, C, and D, projected into a magnetic field directed out of the page. So that means my fingertips has to be pointing out of the page. They say which beam of electrons will initially be deflected towards the top of the page. So they're saying FB is towards the top of the page. That means my palm has to be facing towards the top of the page. Okay, so as you're doing this with me, that means if this is going out, but I want my palm to be facing, I'll just turn around a little bit, pointing upward, that means the only one that matches my thumb is going to be electron A. With electron A, as it enters in, there's a magnetic field pointing out, and so therefore it gets pushed up. The answer is A. A charged particle is moving with a constant velocity. Over here, upon entering a uniform magnetic field, it's going to change its direction of motion. It never changes its speed.